Welcome back to the 90-Day AI Mastery course. Today is day 7, and we are going to explore some of the most fundamental math-based algorithms in computer science, calculating factorials and generating the Fibonacci sequence. These two classic numeric problems are excellent for strengthening your loop logic. Almost every software engineer encounters them in coding interviews, and they are foundational for building AI math libraries. Today, you will learn how to write clean, iterative loops to solve these problems, trace loop variables step by step to see exactly how memory updates, and compare the performance benefits of loops over recursion. Let's dive in. Let's start with factorials. In mathematics, the factorial of a non-negative integer n, written as n followed by an exclamation mark, is the product of all positive integers less than or equal to n. For example, 5 factorial equals 5 times 4 times 3 times 2 times 1, which evaluates to 120. By definition, the factorial of 0 and 1 is always equal to 1. Programmatically, we calculate this by setting a running total variable to 1, and then running a loop that multiplies this total by each consecutive number up to our target. Let's see the Python loop code. Here is the Python loop implementation for factorials. We want to find the factorial of 5, so we initialize n to 5. We set a variable named factorial to 1, which will accumulate our product. Then, we write a for loop using range starting from 1 up to n plus 1. Inside the loop, we multiply our running factorial variable by the loop counter I using the multiplier assignment operator. By printing the current values on each iteration, we can watch how the product builds up step by step. When the loop ends, we print the final result, 5 factorial equals 120. To truly master programming, you must learn to trace your code. Tracing means tracking the state of your variables in memory as the code executes line by line. Let's trace our factorial loop. Before the loop starts, factorial is 1. In iteration 1, I is 1, so factorial becomes 1 times 1, which is 1. In iteration 2, I is 2, and factorial updates to 1 times 2, which is 2. In iteration 3, I is 3, and factorial becomes 2 times 3, which is 6. In iteration 4, I is 4, leading to 6 times 4, which is 24. Finally, in iteration 5, I is 5, and factorial multiplies to 120. The loop terminates, saving the final product in memory. Now, let's explore the Fibonacci sequence. Named after the mathematician Leonardo Fibonacci, this sequence is a series of numbers where each number is the sum of the two preceding ones. The sequence starts with 0 and 1. So, the third number is 0 plus 1, which is 1. The fourth is 1 plus 1, which is 2. The fifth is 1 plus 2, which is 3, and so on, generating the sequence 0, 1, 1, 2, 3, 5, 8, 13, 21, and onwards. Fibonacci numbers are found everywhere, from flower petals to financial algorithms. To generate them in code, we must track the two previous terms and update them iteratively. Here is the elegant Python code to generate the first 8 Fibonacci terms. We start by initializing the first two terms. Variable A represents the current number set to 0, and variable B represents the next term set to 1. Inside the for loop, we print the value of A. Then, we perform a simultaneous assignment swap. We set A to B, and B to A plus B. This single line of Python code is incredibly powerful. It calculates the next term and shifts our tracking variables forward in memory at the exact same time without requiring a temporary third variable. Let's trace how these variables change on each iteration. Let's trace the Fibonacci loop to see how Python updates the variables. In iteration 1, the loop prints the current value of A, which is 0. Then, the swap assignment sets A to B, which is 1, and B to 0 plus 1, which is 1. In iteration 2, it prints A, which is now 1. Then, A updates to B, which is 1, and B updates to 1 plus 1, which is 2. In iteration 3, it prints A, which is 1, and updates A to 2 and B to 3. By the time we reach iteration 6, it prints 5, updating A to 8 and B to 13. This clean iterative state progression keeps updating the sequence in a memory-efficient manner. You might wonder why we use loops instead of recursion, where a function calls itself, to solve these problems. While recursive code looks neat on paper, it has significant performance drawbacks. Every recursive call creates a new frame on the system call stack, consuming memory. If n is large, recursion can cause a stack overflow error. Furthermore, a simple recursive Fibonacci function has an exponential time complexity of O of 2 to the power of n because it recalculates the same values repeatedly. An iterative loop, on the other hand, runs in linear time complexity of O of n and uses constant auxiliary space. For production AI applications, loops are almost always the preferred approach. For today's coding exercise, let's look at a practical challenge: finding the largest number whose factorial is under 10,000. We initialize limit to 10,000 and start our counters at 1. We write a while loop. Before entering each cycle, the loop condition checks if the next multiplication will exceed our limit. Inside the loop, we increment number and multiply our running total. When the loop completes, it prints the result. The largest number is 7, and its factorial is 5040. If we went up to 8, the factorial would be 40,320, which exceeds our limit. This shows how loops help solve numeric boundaries dynamically. Fantastic job! You've completed day 7 of the AI Mastery course and mastered classic loop programs in Python. Let's recap what we learned today. First, a factorial is computed by multiplying a sequence of consecutive integers. Second, the Fibonacci sequence is generated by shifting two tracking variables using Python's swap assignment syntax. Third, tracing variable states helps debug logic and understand execution. Finally, iterative loops run faster and use less memory than simple recursive functions. Tomorrow, on day 8, we will continue loop practice by coding algorithms to reverse numbers, count digits, and check for palindromes. Don't forget to like this video, subscribe, and code these exercises. See you tomorrow.